Welcome to Tomorrow Unveiled. This week, we're really digging into something the research team's been calling the Green Code Hot Core Thesis. And it confirms what many are seeing, that the global energy transition, it's not just a straight line towards putting up more solar panels and wind turbines. It's actually much more complex, a strategic kind of high-stakes bet on two different types of infrastructure working together.
That's absolutely right, yeah. What our dedicated research team has really zeroed in on over the past week is this necessary and frankly accelerating strategic dual deployment. So on one side, you've got the green code. Think of these as the essential low density sources, the variable ones like solar and wind. They're absolutely critical for providing the sheer volume of decarbonized energy, usually spread out over large areas.
Okay, the bulk energy part. And then the other side is the hot core. This sounds intense. This is the high density stuff, right?
Wow.
The firm, reliable power sources. So we're talking things like advanced nuclear, maybe next-gen fusion down the line, and enhanced geothermal.
Exactly. These are absolutely non-negotiable. You need them for grid firmness, keeping the lights on reliably, and for industrial resilience, plus just delivering the sheer energy density that, well, our modern, increasingly electrified economy absolutely demands.
Right. And the big driver here, the sort of central problem that this dual approach is trying to solve, it's not just climate change anymore, is it? It's this explosion in demand.
Precisely. It's exponential demand growth. And look, the Green Code has hit some amazing milestones, fantastic news, and we'll definitely get into that later. But at the same time, you've got this really aggressive expansion of energy consumption happening. And it's particularly driven by things like artificial intelligence, these massive data centers springing up everywhere.
The AI factor, yeah.
And that demand, it amplifies the urgent need for these hot core solutions. Because this digital demand, it's what we call inelastic. It just can't tolerate dips or interruptions. And frankly, it's moving faster than a lot of the current deployment schedules for reliable power.
That sense of urgency really comes through in the research. And it's why we've structured this deep dive on Tomorrow Unveiled the way we have. We've basically pulled together and cross-corroborated evidence on the biggest breakthroughs, really just from the past week or so, from all over the world. We want to give you a really clear synthesis of how fast things are moving.
Yeah, our mission today is sort of threefold, focusing on these interconnected areas based on what the team compiled. First, we're going to explore what's basically a commercial supernova, the AI Nuclear Nexus. We're seeing this massive acceleration in small modular reactor SMR deployment, and it's being driven by, well, industrial buyers.
Okay, AI and SMRs. Got it.
Yeah.
What's second?
Second, we'll shift gears a bit, look towards the scientific frontiers. We're examining some really pioneering advances in fusion energy and also enhanced geothermal, really pushing the limits of energy density there.
Fusion and deep heat. Okay.
And then finally, and this is crucial, we have to take a critical, a necessary look at sustainability. We need to consider the full life cycle emissions of these high-density solutions. And we've got a fascinating, maybe slightly sobering, real-world case study from right here in the U.S. to illustrate that.
Okay, let's jump into that first part, the AI Nuclear Nexus. I have to say I was genuinely surprised by the headlines this week. It seems like advanced nuclear is suddenly being driven by immediate hard dollar deals from data centers, not just, the usual long-term plans from utility companies. How did the AI sector become the single biggest commercial driver seemingly overnight?
And it's fascinating, isn't it? It really boils down to this concept of inelastic demand. That's probably the biggest financial insight from the sources our team analyzed this past week. You see, traditional electricity demand, it has some flex, right? You at home might wait to run the dishwasher, or maybe factory adjusts its output slightly based on power prices.
Sure, makes sense.
But think about running a massive AI training model. Or, servicing thousands of real-time search queries.
Yeah.
That computation, you just cannot tolerate interruptions. Even a millisecond flicker in power, that can halt the entire process. You're talking potentially millions lost in time and data. It's just not acceptable for them.
Wow. Okay, so the tolerance for error is 0. And the scale of this demand, it's huge, right?
Oh, it's staggering. Our dedicated research team, they're projecting that the AI sector's electricity consumption alone is going to surge by something like 160% by 2030. Now, to put that number, 945 terawatt hours annually into context, that's roughly the entire current annual electricity consumption of a major industrialized country like Germany.
Wait, just the AI sector needs as much power as Germany in 6 years?
That's the projection, yeah. One sector, the whole new Germany's with a power demand.
That's mind-boggling.
And that power absolutely must be continuous. 24/7, 365, no interruptions.
The analogy we've been using here really helps, I think. illustrate the difference between the green code and the hot core solution for these specific users. Okay, let's hear it.
So think of traditional grid power. Largely, the green code, it's kind of like relying on a public bus system. It's generally affordable. It covers a lot of ground. But, if the weather turns bad or there's a traffic jam, your delivery schedule gets messed up, you might get your package late. It's variable.
Right. Unpredictable sometimes.
But these massive data centers, what they need is total reliability, security, and often proximity. They essentially need a private, uninterruptible power supply. It's like having your own dedicated bespoke power generator bolted right onto your server rack.
Ah, okay. So that dedicated continuous 247 power source, the
Yeah.
one that gives predictable output no matter what's happening outside, that's advanced nuclear for them.
That's increasingly the conclusion they're reaching, yes. And this demand, it's really driving procurement now. We're moving past the white papers and seeing actual contracts signed. We have two really key case studies just from the U.S. market that confirm this strategic pivot.
Okay, case study one.
Case study one involves a major global data center player, Equinix. They've made a huge tangible commitment. They've actually agreed to pre-order 20 microreactors from a company called Radiant Nuclear. These are their 1 MW Kaleidos units.
20 microreactors. Wow, that's not a pilot project, that's a serious deployment. And the in SMR small modular reactor, that suddenly seems really important here, doesn't it? For the customer, I mean.
Exactly. These microreactors are designed to be genuinely distributed, highly scalable. At just 1 megawatt electric each, Equinix isn't waiting around for some giant centralized plant to maybe get built years down the line. They're looking at integrating nuclear power directly into their operational planning, almost on a site-by-site, rack-by-rack basis potentially. They can secure the power they need for future expansion in specific locations, achieving, true site independence from grid constraints.
That's a big shift in thinking. Okay, that's Equinix. What's case study two? You said it was even bigger.
Yeah, this one is, well, it's mind-boggling in scale and complexity, really. A massive strategic partnership has just formed, specifically aimed at accelerating SMR deployment in the U.S. And they're talking about mobilizing up to $50 billion in public and private investment.
50 billion. Okay, who's involved in this mega deal?
It's an industrial alliance of some real heavyweights. You've got X-Energy, they're the SMR developer with their X100 reactor, but the really critical partners here are Amazon.
Amazon, okay, the cloud giant.
Yep. Then you have Korea Hydro and Nuclear Power, or PHNP, and Doosan Enerbility, another Korean industrial giant.
Okay, so X-Energy, Amazon, KHNP, Doosan. How does that $50 billion commitment break down? What are their roles?
Well, that's the genius of the setup, really. Amazon acts as the absolutely crucial, creditworthy off-taker. Basically, they're guaranteeing they'll buy the power through long-term agreements.
Yeah.
That provides a secure, predictable revenue stream for decades, which bankers love.
Right, guaranteed customer. Makes financing easier.
Hugely easier. Think KHNP, they're one of the most experienced nuclear operators in the world. They bring that deep operational know-how, the regulatory expertise, essential for actually running these things safely and getting them sited.
Okay, the operators. And Doosan.
Doosan Enerbility is one of the world's top manufacturing and heavy equipment firms. They provide the industrial muscle, the scaling. They build the heavy components. So you see, it's not just a promise, it's this fully integrated supply chain. You've got the tech provider, X-Energy, backed by the financier and customer, Amazon, the experienced operator, KHNP, and the manufacturing and construction powerhouse, Doosan.
Wow. That really does cover all the bases, doesn't it?
It absolutely changes the whole bankability equation for these X100 SMRs they're targeting.
Yeah.
They're basically shifting these reactors from being just components of, say, public utility infrastructure, which often carries political risks, debates about rates, that sort of thing, to becoming critical private digital infrastructure projects.
Not like fiber optic cables or cell towers, but for power.
Kind of, yeah. By securing that corporate backing, that balance sheet strength from Amazon, the financial risk profile just drops dramatically. The investment is secured by guaranteed commercial revenue, which is just far more attractive to private capital than relying on, future decisions by utility regulators.
And this model, this private infrastructure approach, it's likely to be copied elsewhere, right? You mentioned Europe.
Exactly. It's creating international blueprints. We're seeing Europe adopting a really powerful template specifically around co-locating these facilities. Just this week, there was a Swedish memorandum of understanding announced. It involves Blykalla, which is developing a lead-cooled SMR, a data center company called Evrock, and Studsvik, which is a nuclear research center.
Co-location, so putting the reactor right next to the data center.
Pretty much. They're exploring putting these lead-cooled SMRs, the sealer design, directly next to hyperscale AI data centers, and crucially, doing it on Studsvik's existing licensed nuclear site.
Ah, that's clever. Skips a lot of hurdles.
Decades of red tape, potentially. It bypasses the immense challenge of licensing a brand new nuclear site from scratch, and at the same time, it secures that reliable, dedicated power source right where it's needed. It's sort of the definition of commercial viability, isn't it?
Yeah.
You've got a licensed site ready to go, paired with a guaranteed high-value customer right next door.
Yeah.
And, that intense commercial pressure, we were just talking about the huge private investments, the focus on guaranteed offtake and deployment that leads us straight into the next, maybe more brutal truth here. The global race in energy, especially for these advanced systems, has decisively shifted. It's moved past just having the most innovative design on paper. We're now deep into the far more challenging phase of industrial execution. Can you actually build the thing?
Right. Logistics are suddenly king. It's not just, can you design a cool new reactor? It's, can you build it reliably, on time, on budget, again and again? That's the whole point of modular, isn't it? But we've heard promises before, right? Big consortiums talking certainty, then schedule slip, cost balloon. So this new strategic alliance between GE Vernova Hitachi GVH and South Korea's Samsung C&T, what makes this genuinely different for deploying their BWRX 300 SMR? Is this just another promise?
That's the absolute critical question, you're right. And the core confidence here, I think, lies almost entirely in Samsung C&T's proven track record. Specifically, everyone points to their role in delivering the UAE's Barakah nuclear power plant. Barakah is pretty much globally recognized now as the benchmark for delivering a large nuclear project on time, on budget, using a standardized approach. That's something, frankly, Western nuclear projects haven't managed consistently for decades.
Okay, Barakah. So what did Samsung actually do differently there? And more importantly, why should we believe they can replicate that success globally? I mean, building in the UAE is one thing, but deploying in places like Poland or Estonia, which are key targets for this alliance, they have totally different regulatory hurdles, political landscapes, right?
Yeah, great points. The key factor at Barakah wasn't just, throwing money and people at it. It was about extreme standardization and adopting an industrialized construction methodology. They essentially treated the reactor complex build like a factory assembly line, as much as possible. Samsung C&T brings decades of global experience in managing hugely complex, large-scale industrial projects. Think massive ports, LNG terminals, huge infrastructure builds. They applied that discipline to the nuclear build-out. They focused on minimizing site-specific customization, relying instead on repeatable, quality-controlled processes, often using prefabricated modules built off-site.
Okay, factory mindset applied to nuclear.
Exactly. And this new alliance is designed specifically to leverage that proven expertise. It directly targets the biggest historical risk factor that has plagued nuclear power for so long. Those massive construction delays and the killer cost overruns that result.
So this industrial block, you've got the American design, the Japanese technology partners and Hitachi, and now this proven Korean execution capability. They're explicitly aiming for global deployment outside North America. You mentioned Sweden aiming for maybe 5 BWRX 300 units there, plus looking at Poland, Estonia. It really feels like a statement that the future of nuclear deployment is all about logistics and manufacturing prowess now.
I think that's exactly right. And importantly, this industrial scaling effort isn't happening in a vacuum. It's being actively encouraged, even pushed, by governments. We're seeing a really profound policy shift occurring. Governments seem to be moving away from just being passive regulators, simply granting permission if you jump through enough oops, towards taking a much more active role in promotion. They're actively working to de-risk these huge investments for private industry.
Yeah, we saw a couple of really good examples of that policy shift just this week, didn't we? Both focused on cutting down that regulatory uncertainty that cost developers so much time and money up front. First, over in the UK, the government opened up a public consultation on what they call the regulatory justification for the Rolls-Royce SMR design. Why is clearing that specific hurdle, this sort of societal benefit question, why is that so crucial for a developer like Rolls-Royce?
Because those initial high-level hurdles are often the most politically fraught and, frankly, the most expensive to navigate before you even know if you have a real project. Regulatory justification is essentially the government's preemptive assessment. It confirms that, yes, this type of technology is considered acceptable in principle for use in the country. It acknowledges a net public benefit. Getting that assessment done early, before you even think about specific sites, clears a massive high-level obstacle. It sends a powerful signal to the global capital markets. The UK government is serious and committed to this specific technology class. That dramatically de-risks the tens of millions of dollars developers have to spend before the first shovel even potentially hits the dirt.
Right, it's like a big green light from the top. That's a huge boost psychologically and financially. And then secondly, back in the US, we saw state-level incentives really showing that advanced nuclear, especially these smaller reactors, is being viewed as a strategic industrial asset now, not just another power plant. There was that Illinois announcement where nanonuclear energy is set to receive, what was it, $6.8 million in tax credits.
That's right, $6.8 million through the Rive, Illinois program. And it's specifically to help them establish a manufacturing and R&D hub for their Kronos microreactor.
And getting that kind of state support is really significant, isn't it? Especially in a state like Illinois, which, as our research team noted, had moratoriums on building new large reactors for decades.
Hugely significant. It demonstrates that states are waking up to the fact that these microreactors, and maybe SMRs too, represent an immediate viable asset for their industrial strategy. They're not just thinking about electricity generation anymore. They're viewing this as a supply chain opportunity, a source of high-skilled manufacturing jobs, a way to potentially revitalize old industrial sites. And they're using targeted financial tools like these tax credits to try and build a domestic supply chain base today, not waiting a decade for it to maybe happen on its own.
So government stepping in to nudge the market and build capability. And finally, just to kind of underscore why all this policy streamlining and industrial focus is happening right now, Duke Energy's latest resource plan, that plan, unveiled this week, seems to confirm the massive underlying demand growth that's forcing everyone's hand, doesn't it?
Absolutely. Duke's plan explicitly includes options not just for SMRs, but also potentially for new large light water reactors. And it's all aimed squarely at meeting their projected demand growth through 2037. It just reinforces the point. The need for large amounts of firm, reliable, clean capacity isn't theoretical anymore. It's becoming a foundational infrastructure requirement for utilities.
Okay, let's pivot now. We've talked a lot about fission, SMRs, the commercial side. Let's look towards the deeper, maybe longer-term frontiers of that hot core idea, specifically the really high-density solutions offered by fusion and enhanced geothermal. Now, these are still, further out compared to SMRs starting construction soon, but our dedicated research team confirms that critical scientific progress here is definitely accelerating too.
Yeah, absolutely. On the fusion front, the ultimate goal is still, bottling a star, capturing the power of the sun's core right here on Earth. And we saw some really significant strides recently, both in plasma performance and, crucially, in control. Over in Germany, the Wendelstein 7X Stellarator, that's the one that looks like a complex, kind of beautiful, twisted donut reactor, it achieved a major new world record.
Okay, what was the record?
They managed to sustain a super hot fusion plasma. We're talking incredibly high temperatures for 43 seconds. That's the longest duration ever achieved at those specific plasma parameters in that type of device.
43 seconds. Okay. Now, the Stellarator design, it's less familiar to most people than the tokamak, right? The sort of magnetic bottle design we usually hear about. Why is achieving sustained operation in a Stellarator so scientifically important, especially compared to the sort of pulsed operations we often see in tokamaks?
That's a great question. It really comes down to inherent stability and the potential for steady-state operation. Tokamaks, while maybe simpler conceptually to build initially, require constant, really complex active control systems to keep the plasma contained and stable. It's like constantly juggling. The Stellarator's magnetic field, however, is designed from the ground up using incredibly complex magnetic coils, hence the twisted donut shape. This complex field inherently offers better plasma stability.
So it's naturally more stable, less juggling required.
In theory, yes. That makes it potentially a stronger candidate for the kind of continuous 247 power generation you'd need from a commercial power plant. You want something that can just run steadily. So achieving that 43-second sustained duration, it's a really important validation of that pathway towards eventual steady-state commercial operation for Stellarators.
Okay, that makes sense. And what's also really exciting here is how the tools from the green code side, specifically AI, are now being used to actually guide the hot core research in fusion. You mentioned scientists at the Princeton Plasma Physics Lab unveiling a new AI system.
Yeah, this is fascinating. It's called Diag2Diag. It's proving to be a massive acceleration tool for fusion research. Essentially, Diag2Diag acts as a kind of virtual sensor. You have to understand, fusion plasma is incredibly hot, incredibly complex. No physical sensor can just be stuck inside the reactor core to measure everything directly.
Right, it would melt instantly.
Exactly.
Right.
So what this AI system does is take the existing, maybe lower resolution data that can be gathered from multiple sensors around the edge of the plasma. And it uses that to generate incredibly high-resolution predictive data about what's actually happening deep inside the complex plasma. It fills in the gaps where physical sensors just can't go or can't survive.
Mhm.
AI is basically solving these immensely complex physics problems, predicting plasma behavior in near real time. And that's potentially accelerating the research by years, maybe even decades.
Wow. AI is a virtual probe into the heart of a fusion reaction. That's pretty cool. And it seems like the commercial side of fusion is trying to keep pace with the science, right?
Yeah.
Gauss Fusion in Germany.
Yes. That was another significant milestone reported by the research team. Gauss Fusion completed Europe's first full conceptual design for a commercial fusion power plant. Now, this is still a design, a blueprint, but it signals that the industry is rapidly maturing. They're moving beyond just pure lab experiments and starting to think seriously about what an actual power plant would look like, how it would operate.
Okay, a full design, but we need to be realistic about timelines and costs here, don't we?
Absolutely, we have to view these critically. The Gauss design targets commercial operations sometime in the mid-2040s. It's still, roughly 20 years away. And the estimated cost is huge, somewhere between 15 and 18 billion euros.
15 to 18 billion euros. Wow. Okay, so while the design itself is a big step, that's a massive price tag and still quite a distant target date. How does this conceptual design maybe differ from some of the other ambitious fusion roadmaps we've seen over the years that, well, didn't quite pan out? And what are the big technological hurdles Gauss still needs to crack to make that mid-2040s date seem credible?
I think one key difference is the emphasis Gauss is placing on industrial collaboration right from the start. They're working with established industrial heavyweights now, focusing not just on the plasma physics, but also on the practical challenges like material science, component manufacturing, remote handling the engineering realities. However, the biggest hurdle, arguably for almost all fusion approaches, remains material science. Specifically, designing the inner wall, the first wall of the reactor, that can withstand the incredibly intense neutron bombardment from a deuterium-DT fusion reaction for years, ideally decades, of continuous operation without degrading or needing constant replacement. Gauss, like others, is essentially counting on significant accelerated materials development breakthroughs over the next 10 years or so to really solidify that mid-2040s timeline. That's a big bet, but one they have to make.
Okay, material science remains the big challenge for fusion. Let's pivot now from stellar fusion down to the deep heat within our own planet. We also saw some really interesting breakthroughs in tapping the geological hot core using enhanced geothermal systems, or EGS. Now, the traditional challenge with geothermal has always been pretty simple, right? Just drilling deep enough, especially through really hard rock, to get to where the truly massive energy reserves are.
Exactly. You're limited by basic mechanics, the sheer strength of drill bits. They wear down, they break. They simply fail under the extreme pressures and temperatures you find when trying to drill through hard, crystalline basement rock deep underground. And that mechanical limitation is precisely what this new millimeter wave drilling technology developed by a company called Quaise Energy is aiming to completely shatter.
Okay, millimeter wave drilling. We need the ELI 5 explain. Like, I'm 5 here. How does a millimeter wave just vaporize solid granite? And why is that better than, say, a super hard diamond tip drill bit?
Yeah, think of it less like a physical grinder and more like a massive, highly focused microwave beam, but using millimeter waves, which are higher frequency. Traditional drill bits have to physically grind and crush the rock. They wear down incredibly fast in hard rock, requiring constant, costly trips to pull the drill string out and replace the bit. It slows the whole process down immensely. This millimeter wave tech, developed initially at MIT, uses high-power electromagnetic energy generated by devices called gyrotrons, similar to those used in fusion research, actually to literally melt and vaporize the rock in front of it.
It melts the rock.
Now,
Wow.
it basically creates a hole by removing the rock thermally, not mechanically. This completely eliminates the physical contact with the hard rock, bypassing the temperature and pressure limits that stop traditional drilling. This could allow them to reach incredible depths. They're talking potentially 19,000 meters. That's like 12 miles down.
12 miles deep.
That's the potential. And reaching those depths unlocks access to immense, virtually inexhaustible geothermal heat stored in superhot rock, potentially almost anywhere on Earth. It could fundamentally change geothermal from being a geographically limited resource to a truly ubiquitous, globally viable, high-density energy source.
Turning the whole planet into a potential geothermal resource.
Right.
That's a huge vision. And we're already seeing EGS-enhanced geothermal systems starting to scale up in practice, right? Fervo Energy in Utah.
Yes, Fervo Energy's Cape Station project in Utah is a really important demonstrator for EGS right now. They're using advanced horizontal drilling techniques adapted from the oil and gas industry to create underground reservoirs in hot rock. And that project is reportedly on track to deliver 500 millidelus of continuous 247 power.
500 megawatts continuous. From geoth.
That's the target. And if they hit it, that would make Cape Station one of the largest geothermal installations ever built. It really helps cement geothermal's role, not just as a niche player, but as a potential source of large-scale, high-density, firm renewable power. It's a baseload energy source that doesn't depend on the sun shining or the wind blowing.
Okay, this is fascinating stuff. Before we dive into the really crucial sustainability questions and look at the limits of just relying on the green code, let's just take a quick moment here.
Yeah, absolutely. If you're finding this synthesis of all these energy breakthroughs insightful and you want to help others discover tomorrow unveiled, there are a couple of easy ways you can help us out.
If you're watching on YouTube, please do take a second to like this video, subscribe to Tomorrow Unveiled if you haven't already, and maybe even consider hitting that new hype button apparently that helps us reach more viewers. And of course, make sure you turn on notifications so you don't miss our future updates on, well, the future.
And if you're listening on an audio platform, maybe Apple Podcasts or Spotify, we would be incredibly grateful if you could leave us a rating and perhaps a quick review for Tomorrow Unveiled. It honestly makes a huge difference in helping new listeners find the show.
I genuinely love hearing your thoughts, too. So whether you're on YouTube or your favorite podcast app, please do leave a comment. Let us know what you think about that Calistoga microgrid case study we're about to get into, specifically its true carbon footprint. Is the local benefit enough, or does the whole supply chain absolutely have to be green? We really want to know your take. Okay, that discussion about deep geothermal and fusion naturally brings us right to the sustainability question, doesn't it? As these high-density energy sources like advanced nuclear and geothermal really start moving towards deployment, the conversation has to mature. It can't just be about, zero operational emissions. We have to look at the full picture, the entire life cycle, including things like resource intensity and especially land use.
Absolutely. And the land use efficiency argument for high-density sources, particularly nuclear, is a really critical sustainability point that often gets overlooked in the debates. Nuclear's energy density is just unparalleled. It means it has an incredibly minimal physical footprint on the landscape. Our research team confirmed the figures. A single Rolls-Royce SMR, the 470 milliredesign design, would occupy roughly the area of just 2 football pitches.
2 football pitches for nearly half a gigawatt of power. That's tiny.
It's incredibly small compared to the alternatives for firm power. And the analysis shows that nuclear requires something like 34 times less land per unit of energy generated than a comparable utility-scale solar PV installation would need to produce the same amount of electricity over a year.
34 times less land. And that density benefit, it's not just about saving acreage, is it? It has knock-on effects.
Huge knock-on effects. Less land use means shorter transmission lines are needed, which saves materials and costs. It means less overall material throughput for the civil engineering works. Critically, it means less habitat destruction, less impact on biodiversity. And frankly, it often means less public pushback on siting because the visual and environmental impact is so much more localized. Density itself is a massive sustainability benefit.
That's a really important point. And are the developers also learning from, let's be honest, some of the historical issues with older, large nuclear plants when it comes to the end-of-life phase, decommissioning waste?
Yes, definitely. It's another key evolution highlighted in the research. Modern SMR designs, and this applies to both the Rolls-Royce design and the BWRX-300 we discussed earlier, are explicitly integrating things like prompt dismantling, standardized decommission procedures, and strategies for minimizing radioactive waste generation right into the initial design phase. They're trying to solve those long-term legacy concerns from the very beginning by making the entire structure inherently more modular, easier to take apart safely, and designing components with end-of-life handling in mind.
Okay, designing for disassembly, that makes sense. Now let's turn to that critical real-world example you mentioned earlier, the Calistoga Resiliency Center up in California. You said it perfectly illustrates this crucial difference between achieving a positive local environmental benefit versus looking at the full global life cycle impact.
Exactly. The local story in Calistoga is undeniably positive. It's driven by very real concerns about public health and community resilience. The system itself is a hybrid, using batteries paired with hydrogen fuel cells. And it was deployed specifically to provide backup power for this remote town, which is unfortunately very prone to wildfire-related public safety power shutoffs. And critically, from a local perspective, it directly replaced these noisy, highly polluting diesel generators that the utility used to have to deploy, literally right in the middle of a community dog park during those fire season outages.
Okay, so getting diesel generators out of a dog park, that's a clear win for the local air quality, noise levels, general disruption. Sounds great locally.
It is a fantastic, immediate, local environmental justice win, no question.
Yeah.
However, the critical counter-narrative, the more complex picture, emerged when our dedicated research team dug into the full life cycle analysis, specifically focusing on the hydrogen supply chain for those fuel cells.
Oh, okay. Where does the hydrogen actually come from? It's not made on-site with local solar panels or something.
Yeah. No, that's the crucial point. If it were, it could potentially be classified as true green hydrogen, but it's not. The hydrogen being used in Calistoga is actually produced via electrolysis, splitting water, using electricity at a large facility way over in Georgia. That's over 2,800 miles away. And the electricity used for that electrolysis process, it's drawn from the regional electrical grid in Georgia, which, despite having a growing amount of renewables, still relies on a substantial component of fossil fuels, primarily natural gas and some coal.
Okay, so the hydrogen itself is produced using grid electricity that isn't 100% clean. That's the first issue. What else?
Then you have to factor in the immense amount of energy required just to get that hydrogen from Georgia to California. Hydrogen is tricky to transport efficiently as a gas. So for long distances like this, it typically has to be liquefied. That means chilling it down to incredibly cold cryogenic temperatures, minus 253 degrees Celsius. And liquefaction is a massively energy-intensive process. It can consume up to 30% of the actual energy contained within the hydrogen itself just to turn it into a liquid.
Wow, 30% energy penalty just for liquefaction before it even gets on a truck.
Yep. And then, of course, you have the emissions from the diesel truck transporting those cryogenic tanks 2,800 miles across the country. So when you add it all up, you account for the carbon intensity of the Georgia grid mix used for electrolysis, you add that huge liquefaction energy penalty, and you factor in the cross-country truck emissions. The bottom line is pretty sobering.
Okay, what's the number? What's the estimated carbon intensity?
The research team's estimate is that the electricity finally delivered by the fuel cells in Calistoga, using this specific hydrogen supply chain, has an embedded carbon intensity somewhere in the range of 1,400 to 1,600 grams of co-euro equivalent per kilowatt hour. G-co-euro-wide.
1,400 to 1,600 grams. That sounds incredibly high. How does that compare to, say, the California grid itself or even the diesel generators it replaced?
It's startlingly high. For context, the average carbon intensity of the California grid that this system is supposed to be making cleaner and more resilient, that's typically around 200 grams co-euro, maybe less sometimes. And even a modern efficient diesel generator, while polluting locally, might have a life cycle carbon intensity in the range of, say, 700 to 800 grams co-euro.
So this clean hydrogen solution could potentially have double the carbon footprint of the diesel generators it replaced when you look at the whole life cycle.
Potentially much higher, yes. That's the implication. The Calistoga project achieves that undeniable, very important local benefit: cleaner air, quieter operation, resilience for that specific community during outages. But it appears to achieve it at a potentially massive hidden global carbon cost, simply by shifting the emissions burden far away to the hydrogen production and transport chain. This case study just highlights the absolute critical necessity of evaluating the entire value chain, the full life cycle, for all these emerging high-density energy carriers, including hydrogen, advanced biofuels, synthetic fuels, everything. We have to be rigorous and ensure that our solutions for resilience and decarbonization are genuinely clean across the board, not just locally clean. Otherwise, as you said, we haven't really solved the climate problem. We've just moved the emissions problem somewhere else, maybe somewhere less visible.
That Calistoga example is incredibly illuminating, and it brings us perfectly to our final section today on Tomorrow Unveiled. We need to talk about the complementary reality here, acknowledging the huge achievements of the green code, the renewables, but also understanding their inherent limits. And we absolutely have to start by acknowledging the genuinely monumental success story on the variable renewables front.
Absolutely, we must. The data compiled by our research team, particularly citing the recent Ember report, confirmed a truly historic milestone. For the first time ever on record, global renewable energy generation, that's solar, wind, and hydropower combined, actually surpassed coal-fired generation in the first half of 2025. That is a massive, incredibly encouraging achievement for global decarbonization efforts. It really confirms the sheer volume of investment and deployment that's been pouring into the green code worldwide.
Surpassing coal globally, that's huge. And there was another key finding too, right, about meeting new demand.
Yes. Also critically important, the growth in just solar and wind generation alone was enough to meet all of the increase in global electricity demand during that same period, the first half of 2025. So basically, the world's growing appetite for electricity was satisfied entirely by new variable renewable capacity coming online. Again, fantastic news.
Okay, so renewables are growing incredibly fast, meeting new demand, even overtaking coal globally. That sounds like total victory for the green code, doesn't it?
Well, yes and no. Paradoxically, this very success, this massive influx of variable power onto grids worldwide, actually strengthens the argument for the hot core.
Yeah.
It highlights the need for complementary firm resources. Think about it. The more variable power you inject into the grid, solar surging online rapidly at dawn and then vanishing just as quickly at dusk, wind turbines spinning furiously 1 hour but calm the next, depending on unpredictable weather systems. The more desperate the grid becomes for sources of stability, for inertia, for guaranteed reliability to fill the gaps. This success actually creates a massive structural reliability gap that needs to be filled cleanly.
Right, the variability creates a need for something constant. And that reliability gap, it's not just theoretical, is it? The comparative data we looked at really quantifies it.
It quantifies it brutally. Nuclear power, for instance, has a proven fundamental reliability or capacity factor averaging around 83% globally. That's because its output is based on controlled physics, not the weather. It operates continuously, 247, pretty much year-round, only stopping for planned refueling or maintenance. Now compare that 83% to the inherent intermittent nature of wind power, which has an average global capacity factor of around 35%. And utility-scale solar PV, which globally averages around 25% capacity factor, obviously because it only generates significantly during daylight hours and depends on clear skies.
Okay, 83% for nuclear versus 35% for wind and 25% for solar. Those numbers really matter when you're trying to run a stable grid, don't they?
They matter profoundly. A capacity factor of 25% means that, on average, for 75% of the hours in a year, that solar asset is producing little or no power, relying heavily or solely on those variable sources for critical infrastructure like those AI data centers we discussed, which need 100% uptime, or even just for maintaining the basic inertia and frequency stability of the grid. It becomes incredibly challenging. It often requires keeping massive amounts of fossil fuel generation, usually gas plants, on standby, ready to ramp up instantaneously when the wind suddenly drops or a cloud cover rolls in. We're seeing real-world headwinds now because of this reliance. Things like the IEA recently cutting its forecast for U.S. renewable growth due to grid connection bottlenecks and stability issues, or recurring volatility in European power markets forcing costly fossil fuel ramp-ups to keep the lights on.
So the conclusion here seems pretty undeniable then. High-density, firm power, whether that's SMRs, maybe larger advanced reactors eventually, or enhanced geothermal systems scaling up, it's not really competing directly with solar and wind for providing the bulk terawatt-hours of clean energy.
Exactly. They play different but equally vital roles. Solar and wind are the workhorses for bulk decarbonization. But the hot core sources, nuclear and geothermal, primarily in the near to midterm, they are the essential, clean flexibility solution. They're required to balance the grid, provide that crucial inertia and voltage support, and absolutely guarantee power for critical infrastructure precisely when the sun isn't shining or the wind isn't blowing. The two systems, green code and hot core, they aren't antagonists. They are, or if they need to be, mutually reinforcing components of a truly resilient, fully decarbonized energy future.
Okay, as we wrap up this deep dive here on Tomorrow Unveiled, let's try and consolidate the timelines we've heard about for this high-density revolution, the hot core side of things. It feels like the path towards getting more reliable, firm, clean energy onto the grid is now being measured in, tangible industrial schedules and deployment dates, not just theoretical blueprints anymore.
I think that's right.
Yeah.
Looking at the near term, say the next 5-10 years, the absolute focus is on industrial execution for fission. The first commercial SMRs, like GE Vernova Hitachi's BWRX-300, especially with that new Samsung Construction Alliance behind it, aiming for global deployment, they're targeting initial operations by the late 2020s or maybe 2030 in places like Canada first.
Okay, SMRs potentially online before the end of this decade. What about the midterm?
In the midterm, say out to 2030 and maybe a bit beyond, enhanced geothermal systems look really promising for scaling quickly. Projects like Fervo's Cape Station in Utah, aiming for that large-scale 500 MW output potentially as early as 2026, are demonstrating immediate scaling potential for firm, clean baseload.
And the long term, that still belongs to fusion, presumably.
Yeah, fusion remains a long-term aspiration, but even there, the consensus on commercial viability timelines seems to be shifting, becoming a bit more optimistic perhaps. This is partly driven by that acceleration in private investment we're seeing, and new government action plans providing more support. While significant grid impact from fusion is still likely mid-century, maybe 2050s or later, we're starting to see more credible roadmaps for pilot plants targeting demonstrated commercial viability sometime in the early to mid-2030s now. Still a long way off, but the target dates are inching closer.
So, phased rollout. SMRs soon, geothermal scaling now, fusion hopefully next generation.
That seems to be the trajectory. And I think the fundamental insight, really, pulling together all this week's activity, the commercial deals, the policy shifts, the scientific breakthroughs, is that achieving both our aggressive climate goals and ensuring continued energy abundance. It just requires sustained, really patient commitment. Commitment to the R&D, yes, but also to the deployment of these high-density solutions. And that commitment needs to extend far beyond short-term election cycles or quarterly corporate earnings reports. We need patient capital, and we need patient, consistent policy.
That need for patience, but also urgency. It's a tough balance. And I think building on that, maybe the biggest takeaway for me from everything we've discussed is how the nature of the competition itself has fundamentally shifted. It feels like we're moving past the stage of evaluating which company has the most innovative design on paper or the best physics. Now, the crucial assessment is about who has the most credible industrial execution plan, who can actually deliver.
I agree completely.
With these global alliances forming like GVH and Samsung, with the massive investments being committed by players like Amazon, and these complex supply chains being forged between industrial giants, the real competition isn't primarily technological anymore. It feels like it's become logistical. It's about manufacturing speed and efficiency. Who can actually build the factory? Who can execute the site preparation flawlessly? Who can deliver that reactor or that geothermal facility on time and, critically, on budget?
That truly is the billion-dollar or maybe $50 billion question, isn't it? And the answer to that question, who can execute reliably, that's what will genuinely determine the shape of the global energy landscape heading into the 2030s and beyond.
Absolutely. Well, that's a fascinating place to leave it for this week. We really want to hear your thoughts on this. Whether you're joining us on YouTube or listening via your favorite podcast app, please drop us a comment. Let us know what you think about that strategic alliance between GE Vernova Hitachi and Samsung C&T. Is this finally the model needed to genuinely de-risk nuclear construction globally? Or do you think the historical challenges of delays and cost overruns are still too deeply ingrained? We'd love to hear your perspective.
Yes, please do share your thoughts. And thank you so much for joining us for this deep dive into the Green Code Hot Core theme right here on Tomorrow Unveiled.